So in this video we're going to introduce the idea of a vector space or vector spaces, and then in the second video we're going to go over the properties of a vector space. So here's the idea. If we take an ordered pair, for example 2, 3, and we plot it in the plane, the Cartesian plane, we can also think of that ordered pair 2, 3 as being a position vector that starts at the origin, that has initial point at the origin and terminal point ending at the point 2, 3. So any ordered pair can be thought of as a position vector. And we can write those position vectors either as a row vector or as a column vector. So we think of these vectors as being, we can think of these vectors as being a 1 by 2 or 2 by 1 matrix. Okay? So if we take all possible ordered pairs, so we do all possible x1, x2, where x1, x2 is just an arbitrary representation of some position vector in the xy plane, and we restrict x1 for our purposes and x2 to the real number system. So we take the set of all possible ordered pairs that you can construct using real numbers, then we call that set of ordered pairs a vector space, and the vector space we call it is R2, sometimes referred to as R cross R, like that. It just depends on the situation. So anyways, the vector space R2, all it is all possible ordered pairs of the form x1, x2, where you draw x1, x2 from the real number system. And you can extend this to three-dimensional space. So three-dimensional vector 2, 3, 4 is going to pin down a position in three-dimensional space, and then we can think of that point, that ordered triple in this case, as establishing a position vector whose initial point is again at the origin and whose terminal point ends at the point 2, 3, 4. And what we can do then is, again, either write this as a row vector or as a column vector, depending on what our needs are. And we want to treat these in three-dimensional space as either 1 by 3 or 3 by 1 matrices, essentially. So we have really seen vectors already. So if we take the set of all possible ordered triples, where we draw the components x sub 1, x sub 2, x sub 3 from the real number system, then we call the set of all possible ordered triples the vector space R3. And you could write it as R cross R cross R. So what you want to do is generalize this. So we looked at a two-dimensional space, a three-dimensional space. Well, we really want to generalize to an n-dimensional space. So if we have an n-tuple, so an ordered list of n elements, x sub 1 through x sub n, where we draw those there's n elements in this vector, n elements, and we draw those elements from the real number system. So the set of all possible n tuples, then we call it the vector space Rn. And of course there's no picture to go with this, because in higher dimensional space we're not particularly good at depicting that in pictures, because we exist in three-dimensional space. That's what we perceive, fourth dimension time, but we don't see that, we experience it. So the set of all n-dimensional vectors forms the vector space Rn, and we add vectors just like we add matrices. So the sum of two vectors u plus v is just going to be defined to be the sum of corresponding components, and we're going to define scalar multiplication times a vector just like we've done it for matrices. Again, we can treat n-dimensional vectors as either 1 by n or n by 1 vectors, or matrices, sorry. And so scalar multiplication is just going to be distribute the scalar that you're multiplying by into each of the vector components. And this brings up, to close this video out, this brings up a big idea in mathematics, the idea of closure. And by closure we mean when we take and combine elements with an operation, if we wind up with an element of the same type, then we say that that set is closed under that operation. So what I mean by that is this. If we have an n-dimensional vector plus an n-dimensional vector, the result of taking the addition is another n-dimensional vector. So we say that the set of all n-dimensional vectors is closed under vector addition or matrix addition, because when we take the sum of two n-dimensional vectors, the result is itself an n-dimensional vector. And similarly, scalar multiplication, we say scalar multiplication is closed for n-dimensional vectors, because anytime you multiply an n-dimensional vector u times a scalar c, the result is still an n-dimensional vector. We don't wind up with an n-1 or n+1 dimensional vector. We get back a vector that lives in the set of all n-dimensional vectors.